All right, welcome everybody. So it's a pleasure to welcome our speaker today. It's Vadim Kaimanovich from the University of Ottawa, and he's going to tell us something about coincidence, equivalence, and singularity of harmonic measures. Vadim, please.
Yeah, okay, thank you very much. It's a great pleasure to be again with you, although virtually only. So what I'm going to talk about is a joint work with my former student, Berang Forghani. And what I'm going to discuss is the following situation. So, well, it's always a little bit difficult to promote these topics because they're somehow in between several areas. So here, well, definitely groups will be present very prominently, but also, well, there will be some dynamics and there will be some probability. But still, I do believe that this whole area of research, random walks on group, does belong to group theory. So like nowadays, for instance, one doesn't have to begin with such an apology giving a talk about geometric group theory, although some time ago it would have been considered completely inappropriate for a group theory talk. Okay, so what I'm going to talk about is the following situation. So we are given a group and we are given an additional structure on this group. Well, there is nothing actually extraordinary in this because, well, in group theory, quite often one is given, for instance, a generating set. That's a piece of additional structure. Or in geometry, well, one can talk just about smooth manifolds, but one can also talk about Riemannian manifolds. Well, that's also an example of an additional structure. And I believe that a probability measure on a group is, well, one can consider it just as an element from group algebra without using the word probability at all. So this is, in a sense, a generalization of having a generating set. So if we have a finite generating set, then we can just talk about the uniform measure on that. And if we have an arbitrary measure, well, one can think about it as a generating set where group elements are additionally taken with their multiplicities or assigned certain weights. And it doesn't have to be finite either. Okay, so now we have a probability measure on the group, and let's assume that our group acts somewhere. So the main example will be, of course, the situation when our group is, okay, and now, yeah, it does something which I didn't expect. Okay, yeah. So for drawing, I have to do like this. So the main example is when G is a free group or hyperbolic. And this action space is just the boundary of our group. The, well, the natural boundary, the hyperbolic boundary. Okay, and then the central notion for me today is the notion of stationarity. So as everyone knows, not every group action has an invariant measure. In particular, this is precisely the case in this hyperbolic setup. And then stationarity, well, still allows one to choose a nice measure to deal with. And as everyone knows, having a measure provides a perfect excuse for discarding a lot of points. It's much easier to deal, to work in the measure category. So what is this notion of stationarity? That's just meaning that our measure, boundary measure, which is denoted by lambda here, is invariant in the average. Namely, if I take its translates and take their sum with the weights provided by my distribution, by my measure mu, then I recover the original measure. Okay, and the other notion, which will be new, is roughly mu stationary. By this, I mean that, so I'm talking about a boundary measure. And by this, I mean that this boundary measure is equivalent to a certain truly mu stationary measure. In other words, this notion only depends on the class of our measure. Now, this rough stationarity is different from quasi-stationarity, because of course, if you start with any quasi-invariant measure, then you take its averages, they will still be in the same class. So it's not interesting. But here I'm talking about a property of my boundary measure to be equivalent to a precisely stationary one, to be in the same measure class. Okay, and then, well, one can introduce, well, the notations which I'm going to use. S of lambda is the class of stationarizing measures. So that's a class of measures on the group. And a bigger class is the class of roughly stationarizing measures. Okay, so now one can deal with this notion in two different ways. And the most common way is to fix our probability measure on the group and then study mu stationary measures. Well, that's called stationary dynamical systems. In our model situation, in the case of free or hyperbolic group, actually it is well known and goes back to Furstenberg that such a stationary measure exists, which follows from Krylov-Bogoliubov theorem, and what is less obvious, it is also unique. Now, what I'm going to do today, I'm going to look in the opposite direction. Namely, given a boundary measure, I want to understand whether this boundary measure can be presented as the stationary measure of a certain distribution on the group. Or in a somewhat weaker form, whether I can find a stationary measure in the class of this measure lambda. Okay, so and then, well, why is it useful? Because I will talk about it a bit later in a moment. Knowing that our measure is stationary actually means that it is essentially the measure at infinity of a certain random walk. And therefore, if we want to study our measure, then we can apply pretty developed machinery related to random walks. So it is much more convenient to deal with a measure when we know that it is stationary. So it provides an additional piece of structure. So what are the questions? Well, we start from a certain measure on the boundary, and then, well, I have defined these two classes. Well, are they empty or non-empty? Do they contain measures from particular classes, for instance, finitely supported? Or whether these sets of stationarizing and roughly stationarizing measures, whether they have any structural properties. So, well, there are certain natural operations with measures. Will these operations preserve the corresponding classes? Okay, so one example of such structural properties is provided by what I call a convex convolution algebra. So that's a collection of probability measures, well, which is a subset of the positive normalized elements of the group algebra, or rather of completed group algebra, L1 group algebra, on which I impose two conditions. So it is an algebra with respect to the convolution operation, so that if I have two measures, well, from this collection, then the convolution is also in this collection. It's close to respect to the convolution operation. And the second natural operation which one can do with probability measures is taking their convex combination. So if my set of measures is closed with respect to these two operations, convolutions and convex combinations, I will call it a convex convolution algebra. The simplest example is the commutative convex convolution algebra just generated by a single measure. This algebra just consists of all polynomials with respect to the convolution operation. Okay, so the first observation is that this collection S of lambda, the class of stationarizing measures, is a convex subalgebra. Well, this is very simple. It follows directly from the definition of stationarizing. So here, if I apply not just, if I convolve not with just one measure mu, but with first one measure and the other one, the result of this convolution will still be the same measure lambda. Now, in this language, one can express various other properties. For instance, our boundary measure is invariant if and only if its stationarizing set is the collection of all probability measures. Okay, now, as I have already mentioned, if the action space is compact, then for any measure on the group, there is a mu stationary measure. It means essentially that the convolution operator, which acts on the space of measures on this compact B, has a fixed point, which is a consequence of essentially Krylov-Bogoliubov theorem. Now, if our boundary action has certain contracting properties, I'm not going to define, but our model is the action of a hyperbolic group on its boundary, or of a free group on its boundary. Then in this case, this stationary measure is actually unique. So this result goes back to Furstenberg 50 years ago. Or more generally, one can extend it to boundary actions of isometry groups of hyperbolic spaces. Okay, so now I can change the point of view a little bit. And in this situation, what I can do is the following. I can start with a measure on the group. Then I can choose the associated unique stationary measure on the boundary, and I can look at all the measures on the group which stationarize this measure on the boundary, or roughly stationarize. Okay, so that's the initial setup, the initial notation. Okay, so now I'm going to refer to random walks on groups. So, which are very natural in this context, because what is a random walk? That's just a product of independent increments. So here, the step distribution of my random walk is the measure mu. I sample increments independently from this distribution at each step, and take a consecutive product. So that's what is called a random walk. So that the position of our random walk at time n is precisely the n-fold convolution of our measure. Okay, so now one can look at these issues from the point of view of random walks. Namely, suppose that the space we are talking about is the boundary of a certain compactification or bordification of our group, and we know that sample paths of our random walk converge to the boundary, which is the case again for free groups, or for hyperbolic groups, or even for some more general classes of groups which are like hyperbolic groups. Then in this case, we have the resulting heating distribution, the distribution of the points where our sample path hits a boundary, and this distribution is naturally stationary. Okay. Now, in this setup, the measures we are talking about, they are all ergodic. And therefore, we can say that a certain boundary measure is equivalent to the harmonic measure of the random walk determined by a measure mu, if and only if this measure mu belongs to the rough stationarizing class of this boundary measure. Now, if our harmonic measure is not equivalent, and by ergodicity it means that it is singular, then it means that our measure mu is not in this.
Vadim? I think we lost Vadim. So we seem to have lost our speaker. He will come back. Oh, this happens. Technology.
Just wait. He should reappear.
Yeah, I mean, hopefully he understood that I had a connection, and hopefully it's temporary. If not, I think we have his cursor here, right? So we'll probably make him give the rest of the stocks. Just send Vadim an email, so hopefully realize something is wrong.
Maybe Berhan can call him.
Yeah, or at least text. Yeah, so that's actually. Okay, so it sounds like a bit of bad news. So Vadim actually is having an internet outage with his internet service. So he asked us to wait a few minutes, but if it's not a temporary problem, so we may have to adjourn prematurely, unfortunately. So because. Unless, of course, what we are talking about, unless Behran wants to pick up and continue the talk, which I would be perfectly happy with, but so yeah. Yeah, occasionally technology lets us down. So Joseph, this notion that he was talking about, this roughly, what did he call it? Roughly stationary or whatever. I mean, is it a new notion or has it been around? Because I haven't actually seen it.
I mean, I think he's just talking about whether the measures are singular with respect to each other or not. So if you pick a measure class, I mean, if you pick a single measure, that defines a measure class of all the measures that are non-singular with respect to that measure.
Right.
So, I mean, it's not super easy to know whether two measures are mutually singular or not. I mean, it's somehow, even though that seems like a natural definition, in practice, it's hard to know whether two measures are actually singular or not.
Right. So it's. Might be more about some kind of inverse type questions, which I guess he didn't get to.
Yeah, I mean, so I mean, there's some sort of analogous results for say Riemannian manifolds. I mean, if you take a Riemannian manifold, or of negative curvature, then you can look at sort of Brownian motion on that, and that will give you some sort of hitting measure on the boundary of the universal cover. And so then you can ask, I mean, that depends on the metric. So you can ask sort of, basically they're all, essentially they should all be different. But the, yeah, I mean, I think even, right, yeah, actually, that's a good point. I mean, if you go back to random walks, I mean, take a random walk in the free group, that gives you some hitting measure on the boundary. But in general, different measures just give you different ones, unless they're sort of accidentally convolution powers of the other one.
Right, but I think that so I haven't completely followed, but
yeah, I'm back.
Oh, right.
Back. Okay, so let me share the screen again.
Just a moment. I think
you have to enable me. Yeah.
I may have to enable you again. Yes. Yeah. Very good. So I think you're a co-host again. So try it now.
Okay. Untitled cam. Yeah. Okay. And you should see my whiteboard now.
Yes. Yes.
Okay, so yeah, I think I was interrupted when I started to talk about the singularity conjecture. So that's a conjecture which is still pretty much open, although there was recent progress due to Giulio Tiozzo and his student Petr Kasenka. So what is this? It's the question, suppose we have a compact negatively curved manifold. or even constant curvature, negatively curved manifold, then on the sphere at infinity of this manifold, there is very natural measure class. And the singularity conjecture is that whenever we have any finitely supported random walk on the fundamental group, then the resulting harmonic measure is always singular. So that's precisely the type of the situation I'm talking about. Okay, so so far I have defined my general setup when talking about, let's say, a group acting somewhere. Then I spoke about the situation when we have a hyperbolic group acting on its boundary. And now there is another ramification of this topic. Namely, one can define the boundary actually for any group, provided we have a random walk on this group, provided we have this piece of additional structure, namely a probability measure on the group, which is what is called the Poisson boundary. The Poisson boundary, well, I think I have to skip the definition because, well, it will be, whatever I say will be either too little or too much for those who know and too little for those who don't. Okay, so to sum it up, once we have a group, we have this additional structure, probability measure on the group, then associated to it is a certain boundary space. But this space is defined, it's not a topological space, it's defined in only in the measure category. And that's a space endowed with an action of our group. And since it is a measure space, it comes with a natural measure on it. And this measure is also stationary. So, and this measure is also called harmonic measure. Now, in the situation of hyperbolic groups, we do know that simple paths converge to infinity, no matter what the step distribution is. However, we still do not know whether the resulting distribution on the geometrical boundary is indeed the whole Poisson boundary. We only know that under certain conditions on the step distribution, they have to be not very spread out. Otherwise, well, the Poisson boundary describes all what happens with the sample paths at infinity, or all stochastically significant that happens with sample paths at infinity. So we know that sample paths converge to the boundary. So therefore, the geometric boundary will be a quotient of the Poisson boundary, but we don't always know whether it's actually a bijection. We don't always know whether the geometric boundary completely describes the behavior at infinity. Okay, so now in this setup, when talking about Poisson boundaries, one can talk about their coincidence. So what does it mean? They're defined as measure spaces, and those measure spaces come from the spaces of sample paths. So I will say that two Poisson boundaries coincide if they're just isomorphic as measure spaces endowed with group action. And in the same way, one can say that two Poisson boundaries are equivalent if they can be realized on the same measure space, endowed maybe with two equivalent but not coinciding measures. Okay, so therefore, yet another avatar of what I'm talking about is the following question. Suppose that we have two different measures on our group, two different random walks. When do these random walks have the same Poisson boundary? Or when these random walks have equivalent Poisson boundaries? Or in yet another formulation, suppose we have one reference random walk what are the other random walks which have the same boundary as the given one or equivalent. Okay, so, well, there are simple examples of equivalent but not coinciding Poisson boundaries, like what I have here at the bottom of the page. For instance, if I take the conjugate of my step distribution, then the resulting harmonic measure will be the translate of the original harmonic measure. More generally, if two measures can be presented as products, as convolution products in two different orders, then the Poisson boundaries are equivalent. Okay, so yeah, then again, well, one can formulate this problem when random walks have the same or equivalent Poisson boundaries. Particular case is yet another open problem, widely open problem in this area. Namely, one can single out the situation when the Poisson boundary is a singleton, which means, well, that there are no bounded harmonic functions on the group. And an open problem is whether this property will be satisfied simultaneously for all finitely supported symmetric measures. So I have one finitely supported symmetric measure on a finitely generated group. I know that its Poisson boundary is trivial. Is it true that for another measure like that, finitely supported symmetric, the boundary is trivial as well? That's completely open question, and it also fits in the general setup that I have described. Another question: does the Liouville property, the triviality of the Poisson boundary of two measures, implies that of the convex convolution, of the convex combination, or of the convolution? That's also a completely open problem. Okay, now, okay, there are two parts in this talk. There is a good news and a bad news. So the good news is that we were able to produce a rather big class of measures which would have the same Poisson boundary as the original one. And this class of measures actually forms a convex algebra, although it's not clear whether this will be the whole class of measures with the same Poisson boundary. So this is based on the following probabilistic construction of a stopping time, and this construction actually generalizes previously known examples of measures with the same Poisson boundary. So what were these examples? One is due to Furstenberg 50 years ago, which is the following. Suppose that we have a group and inside we have a subgroup. We run our random walk on the ambient group, and suppose this subgroup happens to be recurrent. Namely, our sample paths will return to this subgroup infinitely many times. Then there is an induced random walk, the induced random walk on this recurrent subgroup, and it has the same Poisson boundary. It has the same bounded harmonic function. That's not hard to see. Another example is well, this construction, which is due to George Willis. He did it in analytic terms. The idea is the following: if our measure is presented as a sum, not convex combination, but really sum of two sub-probability measures whose masses are therefore less than one, then what one can do is the following. One can take the inverse of one minus the first measure, or rather the sum of the convolution powers of the first measure convolved with the second. So from the probabilistic point of view, it corresponds to the following. So we look, first we sample our increments from the first measure until we ultimately sample them from the second measure. So that's precisely what one gets. And yet another example, that's my very old paper, or rather observation from '83, that if you pass from a measure to any convex combination of its convolution powers, then it also has the same Poisson boundary. Okay, so now how do we generalize all these constructions? It's based on the notion of a stopping time. So in all these situations, actually, there is a certain stopping time involved. So what is a stopping time of a Markov chain? Well, that's an event with the following property. You know that it has happened the moment it has happened. An example is the following. Suppose someone gets married for the first time. Then clearly, the moment you get married, you will know that that's the first time you get married. On the other hand, for instance, one can define the following event. Someone gets married for the last time. Then you will know that it was your last time only at the end of your sample path. So you wouldn't know that at the time of getting married for the last time. So that's what's called stopping, or sometimes Markov time. And there is a generalization of this notion of stopping time, which is called random or randomized stopping time. So the idea is the following. One can visualize it in the following way. So we have the tree of our sample path. So we start at time 0 from, okay, now I can insert an additional page, hopefully, between 4 and 5. Yeah, so what is a stopping time? So we start our random walk at time 0 somewhere, and then we choose where we go at time 1. Okay, then at time 1, we choose where to go at the next moment of time, and so on. So our space of sample paths, that's true for an arbitrary Markov chain, naturally forms a tree. Okay, so now what is an ordinary stopping time? An ordinary stopping time is the following. We put a family of cut points on this tree with the following property. So like here, for instance. Okay, so something like this. With the following property, that if you go along geodesic ray, geodesic rays issued from the root of this tree, then eventually almost every geodesic ray will meet a stopping point. So one can say there will be a guard sitting at this point of the tree, which tells you, no, you are not allowed to go any further. So that's ordinary stopping times. And now one can randomize stopping times in the following way. One can think about these guards as being more real-life guards, which can be corrupted, or which are inherently corrupted. So that when you approach one of these guards, then with a certain probability, which depends only on this guard, they would let you through, and with the complementary probability, they will stop you there. So this is essentially the definition of randomized stopping times, and the main result is the following. So if we have just a plain stopping time, then the Poisson boundary will always be the same. Whereas for randomized stopping times, I would have loved to say the same, but unfortunately here we have to impose an additional condition, finite logarithmic moment. And the reason is, once again, these problem that we still cannot describe cannot claim that the Poisson boundary is the geometric boundary even for the simplest random walks. So here I'm talking about the following situation. Let's consider very degenerate case of a random walk. So I am talking about a free semigroup. And I have a probability measure on this free semigroup. Okay, then let's, for simplicity, assume that, well, it's just generated by two generators, A and B. Well, actually, I need to talk about free semigroups with countably many generators, but let's consider just this example. Okay, so we just have the words in the alphabet consisting of these letters, A and B. There are no cancellations whatsoever, and our random walk consists just in concatenating these words. So the boundary behavior is very clear. So we just take the first word, that's our first increment, then we attach the second increment, and so on, so on. Then the product is an infinite word. The question, is it true that it is only this infinite word which completely describes our behavior at infinity? And unfortunately, even in this situation, we don't know the answer. And that's why I have to impose this logarithmic moment condition. Moreover, the question whether this is indeed all possible types of behavior at infinity is open even in the situation when we know that this harmonic measure is actually Bernoulli measure. That's when the letters A and B in this resulting infinite word are chosen actually independently at each step with the same probabilities. It is open even in this situation, and therefore this result, in this result which I have formulated, I have to impose this finite logarithmic moment condition. Okay, so that was, in a sense, positive result. So this is a construction which allows us to produce a lot of measures with the same boundary. However, we do not know whether, once again, when talking about hyperbolic groups, whether that's all. Probably in some situations, one can claim that indeed this construction of using randomized stopping times does produce all measures with the same boundary measures, and in some other situations not. Okay, so that was a positive result. And now I will I will move to the second part of my talk, where I will give you a bad news. This will be a negative result. Namely, I will construct counterexamples to the question which I had formulated. The question about what happens with the Poisson boundaries of convex combinations or of convolutions of two measures. So here the situation is the following. So yeah, we'll be talking actually just about the modular group PSL to Z. And usually when one looks for the simplest hyperbolic group, usually it is the free group which plays this role, because PSL to Z is kind of a bit awkward. One generator is of order 2, the other one is of order 3. It's not exactly symmetric. However, yeah, it is appropriate to quote here François de la Rochefoucauld, who said, "Nos vertus ne sont le plus souvent que des vices déguisés." or more recent reference is Jane Austen, who said, perhaps it's our imperfections that make us so perfect for one another. And actually, it turns out that precisely these drawbacks of the modular group that make it very suitable to constructing counterexamples. So once again, what are the counterexamples? If I'm talking about measures which exactly stationarize the same measure. Okay, let me write it here. Oops, other page. Yeah. Okay, so suppose that I have, I'm talking about a hyperbolic group. Endowed with its boundary, but it also applies to the simplest situations when G is a free group or a modular group. Okay, so suppose I have a measure on the boundary. Then suppose that I know that this measure is stationary for two measures on the group. So I have U1 and U2 on the group, such that each of them stationarizes this measure. No. Okay, then obviously, if I take the convolution, then it will also stationarize the same measure. Yeah, I just apply convolution first with mu2 and second with mu1. The same is if instead of the convolution, I take convex combination. Okay. Now, here I was talking just a certain measure on the boundary and certain measures on the group. But in fact, I do know that in this setup of hyperbolic groups, this measure nu is the unique measure on the boundary. It's the unique measure on the boundary. And suppose I will, instead of the precise coincidence of these stationary measures. So in other words, this property here means that the stationary measure of mu1 coincides with the stationary measure of mu2, right? Now, suppose that instead of this property, I will require weaker property, that their boundary measures, their harmonic measures or unique stationary measures are just equivalent. Are just equivalent. They do not coincide, but they're just equivalent. And now, as before, I take convex combinations or I take convolutions. Will the harmonic measure of these convolutions or of these convex combinations be also in the same measure class? And it turns out not. It turns out that the answer is no. It is not necessarily in the same measure class. And so this is the counterexample, which involves the our poor relative, the modular group, where I will actually use certain disadvantages of the modular group, which turn out to be our advantages. Okay, so this setup is actually very well known. That's very beginning of the group theory. So the modular group PSL to Z, it's isomorphic to the product of two cyclic groups of orders 2 and 2 with very well-known generators of order 2 and 3. And there is a lot of elementary or at least very visible. Like in Canada, we have visible minorities, and this is kind of visible geometry, very visible geometry associated with the modular group. So the transformations, the generators of this modular group, they're actually very nice, very nice. And one of these, okay, I have the formulas here, so I won't read them aloud. So one of the resulting transformations is just the shift by one, right? And the other transformation is the inversion, which sends the positive half line to the negative half line. Okay, and then, well, there is very nice geometry associated with the okay, whom shall I quote? Well, the Ferry fractions, although, well, there is a lot of history behind these fractions. In particular, Hardy was very upset about those fractions being called after Ferry, saying that Ferry is immortal because he failed to understand a theorem which Arro, citoyen Arro, who was active during the times of French Revolution, had proved perfectly 14 years before. And these geometrical structures were discovered and rediscovered many times. Okay, so what is this partition structure? Well, suppose that we, instead of the usual addition of fractions, we operate with what can be called the addition of the future, when we have two fractions, and then we just add the numerators and we add the denominators. And this will be the result of the addition. Okay, starting from 2 points, 0 at infinity, 0 presented as 0 divided by 1, and infinity presented as 1 divided by 0. We obtain then the first intermediate point is 1, and so on and so forth. That's how one obtains these Ferry fractions. And geometrically, well, it corresponds to just decomposition of the boundary of our modular group PSL to Z, which is set of all infinite irreducible words, into two words. Into two halves, in a sense. So the first half consists of the words which start with this order 2 generator, and the second half consists of the words which start from the order 3 generator. And now here, this is one advantage. So actually, our boundary is subdivided into two sets, and it is precisely because of the presence of this subdivision, it will be very easy for me to construct equivalent but not coinciding measures. And the second advantage is that if you look at how these infinite words are presented, then actually it's in a sense, it's better and more convenient than for the free group, because for the free group, we have to deal with the usual constraints. So the irreducibility, meaning that we cannot write two generators which cancel each other next to each other. That's the usual irreducibility rule. Whereas here, what happens is because of the presence of this order 2 generator, our words are actually written in the following way. We have the infinite sequence of these second order generators, which act just like separators. And in between, we have either the third order generator or its square. So in this way, we're actually dealing here not with a Markov shift, but we are dealing with an honest Bernoulli shift, so that we don't have to worry about any admissible pairs when talking about infinite words, because all the admissibility is hidden just in the rule that, well, we start at the beginning, either we have our separator, this order 2 generator, or not. Then we have the third order generator or its square. Then again, we have separator. Then again, third order generator or its square, and so on. So therefore, here we are dealing just with the usual Bernoulli shift on two symbols. One symbol is this third order generator itself, t, and the other symbol is its square. Or the way I write it here, well, it's symbols of sequence of symbols 1 and 2, which encode whether we take t or we take its power. Okay, and now if one looks at all of this from the measure point of view, then it is very natural to consider the measures which were first introduced by Minkowski in 1904, when actually even the very notion of a measure was just being developed. It's 1902 when the first paper of Lebesgue appeared, 1905 when Vitalis' counterexample appeared, first example of a non-measurable set, and so on and so forth. So Minkowski actually defined it in terms of the associated distribution function, but of course, it's just that he didn't have the language. Of course, he was perfectly aware that he was dealing with a certain measure. So what is the measure? We just use this Fairy partition on the positive ray in order to define our measures. So the intervals of the same order in this Fairy partition, they must all have the same measure, which is the corresponding inverse power of 2. And so Minkowski, yeah, he didn't talk about it as a measure. He spoke in terms of the associated distribution function, which he called interrogation mark function. So he found its properties so unusual at that time. Okay, so that's Minkowski measure. So what's Minkowski measure? Minkowski measure is just the Bernoulli measure corresponding to the situation when the powers of our generator t, power 1 and power 2, are taken independently with equal probabilities 1/2. And one can, of course, talk also about the corresponding Minkowski measure class, which consists of all measures equivalent to this one. Okay, and the second class, a little bit wider, was introduced a little bit later in 1938 by Danjois. And what he did is very natural. Instead of the Bernoulli measure with with equal weights, with the weights 1/2 and 1/2, he considered measures with arbitrary weights. So once again, here in these infinite words, these powers, epsilon 1, epsilon 2, and so on, they're chosen independently from the same distribution. In the case of Minkowski, the weights of this distribution are 1/2 and 1/2. We take either t or its square with equal probabilities, whereas in more general case of Danjois, we fix a certain distribution. So we choose t with probability p and t squared with probability 1 minus p. And well, it is actually this Minkowski measure class which provides a counterexample I have been talking about. So indeed, there are measures on our modular group such that their harmonic measures do belong to the Minkowski class, but if we take their convolution or if we take their convex combination, then the resulting harmonic measures will be singular with respect to the Minkowski measure class. So how do we prove this theorem? We prove it by using this Danjois measure class, because it is quite hard to prove singularity. because it means that you have to prove that the measure about which you are talking doesn't have a density with respect to a certain other measure. However, it is much easier to prove this singularity if we actually know that the measures we're talking about, they just belong to a certain family of classes. And then in this case, well, if we know that all these classes are pairwise singular, and we show that our measure belongs not to the Minkowski class, but to the Danjois class, corresponding to a value p, which is not 1/2, then automatically it will imply singularity, because here we are talking about singularity of Bernoulli measures corresponding to different base distributions. And well, I will skip the technical description of the example. It's here on my last slide, but I will just say that here we are using the positive result from the first part of the of my talk. Namely, I begin with the random walk concentrated on generators, whose step distribution is concentrated on generators. And then I apply a certain stopping time. Actually, I apply two different stopping times. And then I know that as a result of applying these stopping times, I will have the same harmonic measures. I can slightly modify the stopping time so that the measure class remains the same. So that's where I use the fact that the boundary of the modular group very conveniently splits into a union of two Bernoulli shifts. So that the measures I'm talking about, they're just convex combinations of the same Bernoulli measure on the positive ray and on the negative ray. That provides me one more parameter, because of which I can easily talk about equivalent measures which are not the same. And then more or less, it turns out that the first choice which we had already brought this counterexample. So this seems to be a pretty general phenomenon, but its generality currently, it's absolutely unclear. It is not even clear whether one can do it just for free groups, or let alone more general hyperbolic groups. Because in this example, of course, the crucial role is played, well, not so much by the fact that the second generator of the modular group has degree 3, but what's important is that one generator has order 2. So essentially, it works for the free product of the 2 with any finite group, with essentially the same argument. So that's an interesting class of groups, which actually, from the point of view of free products, it's too obvious. But, well, once again, let me quote, well, Laroche-Foucault and Jane Austen. So it's precisely because of this ugly second order generator that these groups have this very interesting property. It remains to understand to what extent this property of having an order 2 generator is really necessary for having this phenomena. I would conjecture that probably not. Probably it should be the same for free groups or more general hyperbolic groups. Okay, I'm actually not even over time. Yeah.
All right. Okay, thank you very much.
Okay, thank you.
Okay, thank you, Vadim. All right, are there any questions for Vadim? So
yes, I was going to say PSL2Z is virtually free. So this doesn't help you do it for the free group then?
No, because no, because you see that there are two operations here. So when I pass to the free group, well, I have to use this Furstenberg induction essentially. And yeah, I cannot control these two operations simultaneously, passing to a subgroup and applying these stopping times.
So, and what was the crucial point? I mean, I didn't really completely follow about this generator S having order 2. So,
Okay, because
the project line, you know, so why was that important?
Well,
argument.
It's important to begin with for the following reason. So, suppose we are talking about our beloved free group.
Yes.
Okay, and we talk once again our beloved uniform distribution.
Sure.
Okay, then how do I choose a measure which is equivalent to this uniform measure? Of course, I can take its translate, but
I mean, you still have the partition of the boundary into like 4 pieces, stuff which begins with A, B, A inverse, B inverse. You can just sort of play with this partition, you know, a little bit. I mean, it may...
Yeah, but you see, the point is the following. In this situation for PSL2Z, there is very simple description of the harmonic measure. And this harmonic measure already, if we look at random walks supported just by the generating set, already these random walks provide us examples of equivalent but not coinciding measures. Whereas in the case of the free group, if we are talking about random walks on generators, then actually different distributions on the set of generators, they will give you pairwise singular measures.
Okay.
And here, so one advantage is that because of that, for free, I obtain equivalent but not coinciding harmonic measures, corresponding just to random walks on the generating set. And second advantage is that these measures are also, well, that easier to deal with. They're easier to identify, because here, once again, they're just Bernoulli measures. They're just Bernoulli measures, and well, Bernoulli measures are very identifiable, very easily identifiable.
And
Where,
actually, I mean, that was another point that I didn't really understand. So, in what sense were they Bernoulli measures? I mean, so I didn't completely understand that.
Well, they're Bernoulli measures in the very honest sense. Okay, let me.
So did you convert them into like a binary sequence of zeros and ones? Is that what you meant?
I convert them into sequences, not of zeros and ones, into sequences of ones and twos.
Okay, of ones and twos. So those were the exponents on T. That's what you.
Yes, exactly.
I see. So instead of I see. So that was the point. Okay.
Yeah. So that's two quite convenient technical advantages. Yeah.
Mm-hmm. I see.
But then again, and we don't really understand this phenomenon neither quantitatively nor qualitatively. That's just the first example. And the idea, once again, is the following. So if we run random walk, then that's in a sense a way to feel, to say how we feel our space at infinity, right? So because this harmonic measure is, well, in the case of hyperbolic groups or free groups, this harmonic measure is just the limit of convolution powers. Okay. And now what happens? That I take two measures such that the limits of their convolution powers are equivalent. Okay. And then, well, I pass to the convex combination, and the limit of the convolution powers of this convex combination turns out to be singular. And here, of course, one can ask a lot of questions. For instance, how does the dimension of this measure varies depending on the coefficient in the convex combination and so on and so forth. But the qualitative nature of this phenomenon is completely unclear yet. Because here, well, I was playing certain dirty tricks with this group PSL to Z, and still we don't understand what's the qualitative nature of what's going on. So how would one explain it just from the first principles?
All right. Okay. Are there any other questions for Vadim? Okay. Let us thank Vadim again.
Okay,
Yep.
thank you very much.
Thank you. That was so let me stop the
Okay, now I can stop sharing.